So here we have a problem that says for f of x defined as, and we have a piecewise function, f of x is equal to 1 if x is less than 1, x if 1 is less than x, which is less than 3, and 2 if 3 is less than x, or x is greater than 3 is another way to write this. Show that the limit as x approaches 3 of f of x does not exist. And this is in a section of the contemporary calculus book by Hoffman that's in a list method section. So I'm going to do this using the list method, but I'm going to do it in the method that I usually prefer first, and then I'll show you it in the method that's gone through in the book. So the method that I prefer is to start with an XY chart, and I'm going to take the value of x that the limit is approaching and put it in the middle. So I have, when I'm trying to show that the limit as x approaches 3 of f of x does not exist, I'll start by putting 3 in the middle, and then for numbers smaller than 3 but approaching 3, I like to start by going to the left of x by 1/10. So I'll start at 2.9, and then I want to approach 3, getting closer to 3 incrementally, but not actually getting to 3. So let's go 2.99 and then 2.999. So we're getting closer to 3, but we're not actually getting there. And then similarly, let's put values of x underneath that are greater than 3, but not a lot greater than 3. So I'll start by going 1/10 away and go to 3.1. But then I want to incrementally get closer to 3, but not actually get to 3. So let's go 3.01 and then 3.001. And usually having the three decimal places is usually close enough. You might have to do an extra value or two if it's unclear, but we'll get there if we need to. Okay, so to use this strategy, we want to plug in our values of x into our piecewise function to see what our values of y are in each case. So when x is equal to 2.9 would be in the region between where x is between 1 and 3. So when x is between 1 and 3, the function is just x. So this would also be 2.9 because it's just, we're plugging in 2.9 and that's exactly what it is. So then if we plug in 2.99, we would get 2.99 for x and then 2.999 for x again. So these are all in the region of between where x is between 1 and 3. So that's why I'm plugging it into this part of the piecewise function. Let's skip 3 because the function is not defined for 3. There's no equal to on either one of these. So we're going to skip 3. I'll just put a line there for now. For 3.01, now we've jumped to where x is greater than 3, or 3 is less than x is another way to say that. For this entire region, every single function value is going to be 2, no matter what x is equal to. So this is going to be 2, this is going to be 2, and this is going to be 2 as well, because all of these x values are in the region of x is greater than 3. So now, what we want to look at is what are the values of y approaching as x approaches 3. So as we go from 2.9 to 2.99 to 2.99, that appears like it's approaching the value of 3. And as we go from 2 to 2 to again 2, this one's not changing, so it's approaching 2. So the limit would exist if these two regions on the left-hand side of the value of x that we're looking for and the right-hand side, if these two numbers were equal, then the limit would exist. But when these two numbers are equal, are not equal, as in this case, that means that the limit does not exist. So that's what we're looking for here. We could show it graphically, like we've done these before graphically, but this is showing it kind of numerically in more of a list kind of framework. So now, that's showing it in the method that I would normally use. In the method of contemporary calculus by Hoffman does it a little bit differently in that when we're approaching 3 from the right-hand side, the way that he shows it is that we would have 3 plus 1. So these are all of our x values. We're going to have a lot more of them in this case, so I'll make a bigger table. So we start with the furthest right value would be 3 plus 1, and then we have 3 plus 1/2, and then 3 plus 1/3. So we're making these fractions, the denominator of the fraction, go up by 1 each time. 3 plus 1/4, etc., until we get to 3 plus 1 over n. So this would be as n is getting very large. And then the next value would just be 3. Similarly, the values on the left, we can start, the furthest value would be 3 minus 1, which is 2. And then 3 minus 1/2, 3 minus 1/3, 3 minus 1/4, etc., all the way to 3 minus 1 over n. So if we take a look at these types of values, to simplify, let me move these all over actually. And simplify. So this one would be 3 minus 1 is equal to 2. 3 minus 1/2 is 2.5. 3 minus 1/3 would be 2.33 repeating, or 2.3 repeating. 3 minus 1/4 is, I said that backwards. That would be 2.6 repeating. And then 3 minus 1/4 would be 2.75 repeating, or not repeating, sorry, 2.75, up until you get to 3 minus 1 over n, which would be approaching 3 as n gets really large. But in order to evaluate that, we would need to kind of choose a value for n. So if we assume that n is pretty large, we could call it maybe like 100 or something to that effect. So if n is 100, then this would be 3 minus 1 over 100 would be 3 minus 0.01, which would be 2.99, that kind of idea. So similarly, we could do the same things down here, but because these values are always 2, it doesn't really matter what these numbers are. We don't have to plug anything in. We can just say that all of these values are 2 in this example. And then since these numbers are in the region of x is greater than 3. For these numbers that x is between 1 and 3, they're always the value of x in the function. So this would be 2, 2.5, 2.6 repeating, 2.75, and 2.99. So we're trying to see what are we approaching. It's similar as we have here. What are we approaching as we go towards 3 from the numbers to the left of 3? These numbers are, again, same as last time, approaching 3. We're going from 2 to 2.5 to 2.6 to 2.75, 2.99. We're getting quite close to 3. And then as we approach 3 from the right-hand side, or the values of x that are bigger than our number in question, these numbers are all the same, so we're approaching 2. So again, when these two numbers are not equal, that means that the limit does not exist. So I hope this video was helpful for you. If it was, please like the video and subscribe to my channel if you'd like to see more similar videos on homework questions. If you have a homework question that you would like help on, feel free to leave that in the comments, or I also have my email down in the description that you can email me if you have like a picture that you'd like to send me. Thanks for watching.